Hi, welcome everybody. This is How to Build Distributed Systems in JavaScript. We're at JNation, which is the only conference I know of that's both Java and JavaScript, in Coimbra, Portugal. My name is Loren Sands-Ramshaw. I wrote a book on GraphQL called The GraphQL Guide, and I'm a longtime full-stack web and mobile developer. My first job actually was apropos. It was in 2007, working at a tech startup where we were using GWT, Google Web Toolkit, to compile Java to JavaScript on the front end. It was cutting edge at the time. Enjoyed that framework. Currently, I'm working as a language runtime engineer at Temporal, which we'll get into in a bit. I'll start out with definition of distributed systems, and then we'll look at how to make code in distributed systems more reliable, and then how that becomes much easier with Temporal. And it's not, by no means, all distributed systems, of course, but it is a very general purpose tool, and so has a surprisingly wide breadth of applications inside distributed systems. So the Wikipedia definition of distributed system is a system whose components are located on different networked computers, which communicate and coordinate their actions by passaging messages from one another from any system. So we could think of like my phone going to hello.com and seeing a web page. That's a distributed system because there are two different network computers, my telephone and the one server that's doing the one response. But that's a pretty simple one. There aren't many failure modes. It's like either I can't reach the internet from my phone, in which case I'll retry, or maybe the server's down, in which case I'll retry by refreshing. So usually when we're talking about distributed systems, we're talking about back-end systems with multiple services and communicating among them in our back-end. And so I guess a slightly more complex example is you have a monolith with a single database that supports transactions. So in that case, if we have a business flow where we can do everything in a single transaction, then all we have is the client making a request to the server, and the server talking to the database a single time. And basically, if we get the request and we can't reach the database, then we respond failure, and the client tries again. And then similarly, if the client can't reach the server, they retry. So basically, it's just, it doesn't need to be more complicated than client just keeps retrying. So when we move away from that monolith that I just described into microservices, then the possible failure types increase exponentially, and there are a lot more reliability concerns that come up. So for instance, if we're having like a business process that's first like charge Stripe and then talk to a database, then we get the request from the user, we try to talk to Stripe. If we can't reach them, let's say we send failure to the user. But if we talk to Stripe successfully, and then aren't able to reach our database, like our database is temporarily down or our process fails between those two steps, then we have inconsistent state. Stripe thinks we've charged this person, and our database thinks we haven't. So I guess those are the type of reliability concerns that we come across in service-oriented architecture. And I'm going to go through an example of posting to an orders endpoint to create an order, and we're going to try to make it more reliable. And then we'll see how complicated that gets to try to get it to like full reliability. And then we'll simplify it by using an open source project called Temporal. So this is the first version of the order function. And this is TypeScript, but the only typing parts are like this import type and colon type. So you can ignore that, and then it's just JavaScript. So this is a single serverless function that takes out of the request body the item that the user wants, the number of that item, and the address to go to. And then out of the authorization header jot, we get the user ID. And then we do 3 steps. We talk to the inventory service. We say reserve this number of this item. And then we talk to the payment service, and then we say charge this user. And then we talk to the fulfillment service and say send this package. And in the green success case, this logic works fine. This is like what we want to happen. But the problem is any of these services might be down, or I might not be able to reach them. They might return some kind of error code, even if I am able to reach them. So we need to do a saga. We need to compensate. If we hit an error in the middle, we need to go back and undo the previous steps. So for instance, if we successfully reserve, and then we try to charge, but we fail to charge, we need to go back and unreserve. Similarly, if we successfully do the first 2 steps, and then we try to send package, but that fails, like fulfillment service says, I don't know, some terminal failure, then we need to go back and refund the user, and then unreserve the inventory so that someone else can purchase it. So let's see what that looks like. So this is v2 of the same function. We've added, if this reservation failed, then we just send status 400 to the user. If the reservation succeeded, and we go to here, and the payment fails, then we first unreserve, and then we respond 400 to the user. Similarly, if we get through the reserving and the charging successfully, and we go to the package, and that fails, then we have these 2 compensation steps to undo the first 2 steps. So that's you're probably familiar with this if you are familiar with the concept of a saga. When you're trying to whether you have different services which each have different data stores, and you're trying to eventually get to a consistent state where each data store has a consistent view of the world. It's better for many purposes over like distributed transactions or 2-phase commit, which can be complicated to do right and have low throughput. So next up, let's add some retries and some timeouts. So if any of these service calls fails, ideally I'd like to be able to retry it because maybe it's a temporary network outage, or maybe the service is just down but about to come back up. So I'd like to retry this call a few times. And during each retry, I'd like to have a timeout. So say I send a request and I haven't received a response back in 30 seconds. I'd just like to consider it failed and then try again. So let's implement that. We've added a function called retry. It takes a maximum amount of attempts, a timeout for each call, and an initial interval so we can do exponential backoff. And inside this for loop, let's make this bigger. Until we get to max attempts, we do a race between 2 things, the service call and the timeout. So whichever finishes first, we will either throw an error if it timed out, or break if we get a successful response. If we catch an error either from the service or from the timeout, then we set timeout, or we wait for that interval with an exponential backoff. So we're using this function retry. We pass it this service call. So this gets assigned to this first function and gets called right here. And we're using the default configuration of max attempts and 30-second timeout. And we can do that for each of these service calls. Charge, send package, all wrapping them in a retry. When we start doing retries, one concern we might have is item potency. So we might send the charge command twice, and it's possible that in the first case it succeeded, but I didn't realize that it succeeded. So like I didn't get the response, but the charge went through. So I'm retrying it, but the user's already been charged. I would like to not charge the user again. So the usual way to add item potency is to send a request token from the client to us in this function in the server, and then keep on passing that request ID to each of our backend services so they can check to see whether they've already processed that before they process that request. So we're adding request ID, which is coming from the client. So for instance, like if there's a form on the front end that has all this information, and someone double-clicks the order button, the client would be responsible for sending the same request ID in each of those clicks. Or disabling the button would be preferable, but let's just assume there's some way to like double order on the client that this is helpful for. So we're getting the request ID from the client in the body, and then we're passing it to each of the services: charge, unreserve, and the compensation. So send package, refund, and unreserve. Next up, we want to not just retry the mainline methods, the sending package, etc. We also want to retry each of the compensation functions. So if we add that, then we're just wrapping each of them in retry. So if the payment fails, retry unreserve. If fulfillment fails, retry payment service and inventory service. Next up, let's notice that in the retry function, if we go through max attempts, then we're throwing an error. We might be throwing an error, and we need to catch that. Currently, we're not catching, so we can add that. Catching errors. So here if this retry throws, we're catching it, we're saving the error, and then we're sending that error message to the user each time. And we're also now like correctly doing the retry logic on a throw from the retry. All right, next up, we have an issue where if this process dies between any of these steps, and so some of these steps might take a long time, so it's perfectly possible that the process will die. I want to make sure that I know what the status of this order is so that I can pick it back up from the right place. So for instance, if I successfully reserve inventory and then charge, and then I try to send package and that fails, and then like right here on this line, the process dies. The server gets restarted, or the server loses power, whatever reason. I need to know where I am so that I can continue processing from here. So in order to save state, I need some data store. Here I have MongoDB and different states that the order can be in. So at the beginning of the function, I'll connect to MongoDB, orders database, orders collection, insert a single document with all of the information, and then starting in the created state. And then in each step, I can change which state it is by updating this document in the database. So here we go. If we failed to reserve, we update saying failed to reserve. If we didn't fail, then we update it to reserved, etc. And then we have like different stages for each level of compensation. So here, before we refund, there's a state, and then after we refund, there's another state, and after we unreserve, there's a terminal state. So that's great. So now we know where like an abandoned order is at. But we want to be able to like automatically pick that up and have a process continue processing that. So basically, we need a pool of workers who are polling the database for any document that's not in a terminal state that like hasn't been updated in like an hour, or however the longest amount of time a process might take to like do retries in between steps. And we need to like restructure this function so that we can just, as sort of like a state machine, just like given the current state, execute this amount of code so that the workers are able to like jump to this line, sort of. So we need a worker pool. We need to add like this updated at field. We also ideally would like to return to the user earlier, because with all those retries and timeouts, we might have taken a long time, and particularly we might have exceeded the maximum execution time for the serverless function that we're in. It might be like 30 seconds, I don't know. And also, so technically, our process is going to get cut off before we finish this function in any of the error states. But also, it'd be nicer UX for the client to receive a response sooner. So we might like to respond to the user after we insert the created document, or maybe after we check the inventory, and then sort of asynchronously continue with the order flow. Some other issues that we're not going to go into, but I'll just mention are we need to make sure that our database client is retrying and handling errors, which we're not doing currently. So lots of different things, and let's see what this looks like. This is the whole function that we've written. We've got the database client, the retry function, different states, connecting to the DB, inserting, and then all of the retrying and compensating and state updating. So that's our full function. It's a lot, and let's see how much easier it can be with this open source library called Temporal. So we're importing something called this client that is going to talk to an open source cluster. And similarly, we're in the serverless function, getting data out of the body and auth token. And we're starting this process order function, giving it the information and the arguments, and using the request ID as an idempotency token, is called the workflow ID. And that's it. That's the only step. If we've already started this function, like with the same request ID, we'll get this error. So the system ensures uniqueness of workflow IDs. Let's look at how this process order function is defined and what it looks like. So it's a simple async function, and it does our steps. It says reserve and then charge. And if we fail to charge, we unreserve. And then we send package, and if that fails, we refund and then unreserve. So this is the logic with compensation that we coded before, and this is fully reliable. This is I can code this in a fault-oblivious way, where I don't care, I don't need to know whether any of this is failing, because the system ensures that it will eventually go to completion. So you might be thinking, okay, these functions must be really complicated then. So let's look at those. So these are really short functions, just calling the service with the right information. So I'm not coding any of this retry or timeout logic myself. It's all getting automatically done by the system through this function and configuration. So similarly to these all getting retried, this function is also a durable function in that if it dies at any line, the system knows which steps have happened. It sort of uses event sourcing under the hood for each command, and there's a worker pool that will pick this function back up if the current execution dies. So I call Temporal a durable code execution framework, because it's sort of like you're writing your program and it's being run durably. So the TLDR intro to Temporal is the open source runtime for managing distributed application state at scale. So I guess the idea of this distributed application state is a state that, like we just saw, has to do with any business process or logic that needs to happen across multiple different services, and it works at high scale. It's sort of relatively easy to solve this problem at low scale. There's a lot of complexity in getting it reliable at high scale. Why would we use a system like this? The most valuable mission-critical workloads in any software company are long-running and tie together multiple services. And it's used by by Uber, Netflix, Coinbase, Stripe. And sort of the system requirements that this fulfills and that we generally need in this type of work. Because the work is complex, we want to easily model dynamic async logic and reuse and test and version and migrate. So we need workflows as code. We need to be able to define these business processes, these functions, in code so that we can reuse the code and test it and version and migrate it. Because this work relies on unreliable systems, we want to standardize timeouts and retries. We don't have to code it like we did for each feature that we're adding to our application. And we want to have a reliability on Rails that's available to every team in our org or our company. So we need microservice orchestration. Because this work is so important, we can never drop any work. So we use event sourcing under the hood. The status quo is using some single-purpose system for what I described earlier with the worker pool, a task queue, a Redis for like durable timeouts, and a data store for business data. And you're sort of like connecting all these things with duct tape, and it's hard to get it right and make sure that in all the failure cases, our system winds up in a consistent state. And then Temporal is a general purpose orchestration tool that has sort of three parts. There's the client that starts workflows, which is this process order function that we looked at. And then there's the cloud platform. That's a cluster of services and data stores that allow for that take all the Redis and queues and put it together and operate on them with transactions to maintain consistency. And then we have a worker pool that processes tasks, basically progressing each of these functions or doing the retries of the service calls. So I guess the naive approach is you have 3 different services, and they all need to do different work in this business process. System A just directly calls System B, which directly calls System C. In order to make that reliable, you need to add retries and timeouts at each system or service barrier. And that can become a lot of work, especially when you have a lot of microservices, like Netflix and Twitter have over 500. This is Amazon Web Services' recommended solution for retries between services. It has 3 different queues and a Lambda function and a human operator in the loop. So if you do this between each service, it can get complicated. So at the top we have like the retries and timeouts between each service that can get to be a lot. So what you want to transition to is orchestration on the bottom, where there's one central part of the system that you tell the order of when things should be called, and it does all of the retries and timeouts for you. So there's the other solution people go to is called choreography, and Richardson, the author of Microservice Patterns and Microservices.io, recommends that only use choreography in the most simple of cases, but generally use orchestrators. And I would say that it's even hard to get simple choreography working correctly and reliably. And you probably have more complicated needs, so you might as well just start with orchestration. And then Richardson also talks about the one downside of orchestration is having a single point of failure, but the temporal cluster is extremely fault-tolerant and highly consistent. So if any of the parts go down, whether it's Cassandra or any of the services, they will all start back up and be in a consistent state. And they're also, each of them are horizontally scalable and fault-tolerant. Here's a great article on choreography versus orchestration. On the left, we have different Lambda functions, some of which publish to a message bus, and some of which are listening on the message bus and get triggered. And then on the right, we have an orchestration where there's this central thing controlling when each step is called. And conceptually, it's much easier to visualize and understand the orchestration than it is choreography, especially when we get to the big diagram we saw before. So it's orchestration, I think, in general is easier to understand and reason about, and that's really important for being able to maintain it, add to it, debug it, and have it run correctly and consistently. So the current programming model for orchestration is with markup files, whether it's XML or JSON or YAML. I find that suboptimal. So you're describing logic in either a DAG, like this graph in the middle, or a markup file. And you're saying sort of like, okay, do this first step. Let's say on the left we have first step is an HTTP call, and then we have this next thing called where to jump, and we depending on the result of the first, we have a switch statement, and we either jump to the small step or the medium step or the large step, and they're basically like go-to statements, like we were programming in Fortran, and it's hard to read and understand, and it's much easier to read and understand if you're looking at code. So Temporal's programming model is with code. We have a few different SDKs, including Java and JavaScript, and you can read it and understand what it does. It does the HTTP function on the first line, and then depending on the result, does one of three other HTTP gets. And in addition to being able to just understand it, you can set breakpoints, you can log, you can extract helper functions, etc. So the basic unit of Temporal is a workflow function. So it's in JavaScript and TypeScript, it's a simple async function that returns some value and might call some activities. So activities are any kind of function that talks to the outside world that might need to be retried or that might return a different value. So in order for us to give you the guarantees of reliability and durability of execution of workflow code, it needs to be deterministic. The system needs to be able to replay it on a different worker, replay that function, and have it take the same code path. So the way we're able to do that is separating deterministic code is in the workflow, and then code that is undeterministic, that say does math.random or talks to a disk or the network, that's all in activities. And it's sort of just like, it feels just like calling a function directly. In actuality, it's adding an event to the event sourcing history of this function and like tasking a worker to pick up running of the function. So each of the activities has different timeouts and retries you can configure. By default, the retry policy is infinite. You start with 1 second, goes up to 2, then 4, then 8, and maximum attempts infinity. So the system diagram is sort of like how what it looks like if you deploy and working in the system is the application developers and the platform team are sort of separate. And the app devs use the client that we saw that we put in our serverless function to talk to the cluster and say, hey, start this workflow. And then the cluster is maintained by the platform team, or you can pay us to host it. And that has like the task queues and the timers and everything wrapped together. And then as an application developer, I also host my fleet of workers. And the workers have the definitions of each of the workflows and activities. So looking back at our code, the client function is just used here. So that's this up here we're using inside of a function. And then the workers have both the workflow code, this process order, and all of these activity codes, activity functions right here. So I would give these two, I can show what it looks like. Worker. So I import a worker from the worker package, and I create a worker, and I give it the path to the workflow code, which is right here, and import the activities, which are these functions. I run this worker startup script and deploy a pool of these workers. And they're picking up tasks from the cluster to progress the execution of whatever gets started by the client, so this process order workflow. We just saw a demo of that. There are a number of different APIs we give, one of which is sleep. So this function, we charge a user, and then we sleep for 30 days, and then we charge again. And normally you wouldn't want to do this because the processes will likely not be around in 30 days. Maybe I shut down all existing processes when I redeploy my new code, and that happens every week or so. Or maybe there's just maintenance on my server. In any case, if this was a in-memory timer, it would unlikely to still be around. But the way that Temporal works is that each statement results in sort of a command to the server. And so it doesn't make any difference to us whether this command says, like, start a timer for 30 days, or is it start an activity function. This process might not be around when the sleep timer goes off in 30 days, but it doesn't matter. As long as there's still a pool of workers, they will get that next command, which in this case is like timer fired, and then this workflow function will start again with recorded values for the result of the first charge, and then, okay, the sleep is done, and then it'll start doing the second charge. We can do an infinite while loop with this to do a monthly billing to charge and then sleep until the first of the month. These functions can be long running. They can be forever running, like this one here, where it's like the lifetime of the user. And we might want to get information into this running function, and we might want to get information out of it. So when this signals is getting information into it, here we're updating the amount of the subscription, so how much to charge the user. We can also do a query saying, okay, what's the latest amount of this user? Or I could have a variable saying how many times I've charged them in the past, and I could look that up with a query. Having all these workflow APIs makes it so that we can have a pretty complex project requirement with a trial period that has a cancellation email and a max billing periods and an updatable amount charged and an updatable amount of billing periods. And we can implement that logic in 20 lines of code. There are lots of different APIs in Temporal. We have the server, the cluster that I talked about. We also have dev tools. There's a UI that sort of shows the history of each workflow and the current state. And we also have a command line tool, and then SDKs, Go, Java, TypeScript, /Node, /JavaScript, PHP. We're also working on Ruby, Rust, .NET, Python. Here's a view of the web UI with sort of each row is an event in the processing of this workflow. So here, a timer started, and then it fired after 5 seconds, and then we start the workflow again, and then an activity is scheduled. So one of those activity functions was called. Outcomes of switching to Temporal is more reliable, much fewer incidents, and more productive. It's easier to code, easier to maintain. and easier to operate because it's allows you to observe it very easily, and all of the errors are in one place. It's used for a number of different verticals, including business transactions. Coinbase uses it for crypto transactions. Long-running processes, including with human in the loop, like background checks with Checker. Data pipelines, ETL, Descript uses it for their video transcription. And this is the state, looking at the quote on the bottom left, this is a state that teams can get into with like specific purpose-built systems. We had one incident every week just on the transcription workflow because it was too complicated to maintain. We were afraid of doing any changes on that code path. Infra provisioning is another vertical we're used for. And Mitchell Hashimoto of HashiCorp said HashiCorp needed to build long-running, reliable, fault-tolerant tasks for their cloud platform. Temporal's technology satisfied all of these requirements out of the box and allowed our developers to focus on business logic. Without Temporal's technology, we would have spent a significant amount of time rebuilding Temporal and would have very likely done a worse job. This quote reminds me of Greenspun's 10th rule, which talks about any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, and slow implementation of half of Common Lisp. And Temporal's 10th rule, which isn't actually on Wikipedia, but I just edited the page. Any sufficiently complex distributed system contains an ad hoc, undocumented, unscalable, and unreliable implementation of half of Temporal. So I guess if Hashimoto had built something, it would have been like more specific purpose and less general, and as he said, would have done a worse job. And we find that a lot of companies have built something specific purpose that they're migrating to Temporal from, and it's often undocumented, unscalable, and unreliable. So when to use Temporal? If you ever have important work and reliability is important to you. Don't use Temporal if the work isn't important and you don't need this level of assurance. For instance, like sending marketing notifications or emails when it's fine that it fails occasionally. You also wouldn't want to use Temporal if you need very low latency, like if you're doing trading or gaming, because each step that is taken in the program is persisted to Cassandra. So there's a lot of database writes involved and a lot of like communicating between the worker and the cluster. We have a great team, people from AWS and Microsoft and Uber and Google that have been working on this problem of orchestration and durable code for a long time. We have a great community. I answer a lot of questions on the support forum and the Slack. We also have a YouTube channel with some good videos if you're interested in learning more. And we have a number of companies like Stripe that advertise looking for people with Temporal experience. Our cloud offering is optional. Again, it's MIT licensed open source, so you can host it yourself with Kubernetes, or you can pay us. I guess the value prop is that it'll probably be cheaper to pay us to do it, not even including the salary of the DevOps people that you're employing to maintain it. Here's some slides on sort of how the cluster is implemented internally. So if you have a workflow execution engine, it needs to like get the workflow definition. So this is like abstract and it can include the other orchestrators like Airflow or step functions that use markup language definitions of the workflow. You need to like get the definitions and then execute each task. But you can't do it this way with the engine sort of like calling each one directly. You need a task queue. So here we're adding the queue. So the engine is adding tasks to the queue, and the tasks are getting picked up by workers. Then if you add timers, you have another thing to store. And then you need to have transactions between the state of the workflow and the timers and the task queues. So this is a guarantee that we have in our system. So thanks a lot. We have like 7 minutes for questions. The first link is the docs to the TypeScript SDK, and mailing list, YouTube, Slack, and then all my social handles are on my homepage. And I will also be free after if there are more questions or if you'd just like to chat. And I'll also be at the party tonight. So if there. So we have a microphone if anyone has any questions. Be happy to go into any part of the system or talk about any of the slides. All right.
So if you agree, then we will end it here. So there's still the after party, so please join us downstairs. We have the contacts of Loren if you also can. Thank you for being here today.
Yeah, thanks so much for your time.